Um, okay, so let's get started. Today is our great pleasure to have Professor Mani Srivastava from UCLA to give us online seminar today titled "Efficient Enabling Rich and Trustworthy Inferences at the Extreme Edge." Mani is a well-known and well-established researcher, particularly in many areas, including cyber-physical systems, sensor networks, wireless networking, and embedded systems, and in many others, and particularly Internet of Things in most recent years. So Mani is a distinguished professor at UCLA in the Department of ECE, as well as with a joint appointment in the CS department as well. So he has a very broad research interests and made a lot of contribution across all these areas, including human cyber physical systems, Internet of Things, particularly those systems that are learning enabled, resource constrained, and trustworthy. And he has made a lot of contributions in a lot of applications based on these technologies, such as smart health, sustainable buildings, and smart building environments. And Mani is a fellow of both the ACM and the IEEE. Without further ado, let's give the floor to Mani, please.
Yeah, thank you. Thanks everyone for joining. A real pleasure to visit you remotely, I guess. As my interest have been in, I guess, cyber physical system and kind of various other names that I use to refer to that field. And in recent years, like most of you interested in the area, I guess the big change that has happened is that sort of we have changed gears from working with simple scalar data types and using, if you may, first principles type models from signal processing and physics and whatnot, to kind of very broadly processing data and sort of taking control actions using models which are sort of data-driven, particularly neural network type models and all. And I guess this talk at some level is about sort of having this nexus of IoT, AI, ML, loosely speaking, and some of the challenges sort of occur. What distinguishes some of these problems from their counterpart in the broader AI, ML community, of course, is the physical interaction and the fact you are often in extremely resource-constrained settings, and just the type of modalities which are different. So those are some of the things I'm going to sort of touch upon, and of course, the work that I'm describing is based on sort of lots and lots of collaborations, as well as through some of the centers that I'm engaged in. Now, what characterizes this marriage of AI and IoT really is three things that's happening. First, really a rich view of sensors and actuators that have emerged and which we fund our edge devices. So, of course, camera and sound kind of sensors have always been, but now we are seeing the ability to image, if you may, in other wavelengths, so millimeter wave radars and such, then 3D sensors like LiDAR, and on the actuation side, again, sort of UAV, all sorts of other platforms that have emerged. Second thing, of course, the huge advances in the type of models that we are using. At this point, there's a whole bag of models that exist, ranging convolutional and LSM to the latest transformer type models and all, and ability to kind of pack them into edge devices. And finally, particularly sort of relevant IoT space is the fact that on the edge, we no longer just have simple controls, but often we have accelerators and such. And it's kind of this nexus which is really getting us to some pretty interesting things, but also raises a set of problems. What it's letting us do is really make very complex or rich inferences from relatively simple sensor data. When I started in this sort of my professional journey almost 20 plus years ago, we used to work with temperature sensors and stuff, and kind of the processing used to be so simple. But now if you look around, the kind of activities and events that we seek to infer from even simple sensors like IMUs and a unilateral microphone and such is pretty amazing. The impact this is being felt on how we as humans interact with our devices, wearables and such, as well as kind of the sensors both which we wear as well as sensors in our environment and kind of other things that we have. Cars and UAVs and such are able to infer about us. So in my lab, through a variety of projects, we kind of work broad across the space, health-related inferences, small buildings kind of things, as well as a lot of work relates to military as well as underwater kind of an application. But one sensor that we, on the simple sensor side that we squat a bit on is movement-related sensors and physiological sensors and making all sorts of inferences around it. The second thing that this marriage is letting us do is to really for deeper analysis of the scenes that we have. So normally, sort of, we rely on things like cameras to analyze the scenes, but with the kind of sensors that we have now, combining RF, cameras, of course, and acoustics, we can really create very interesting understanding of the scene. So not simply what objects are there, but also things about their internal state, for example. So in a work that we had presented at just a few months ago, things like, is an appliance on off, even though visually it looks the same, but we can through remote vibrometry kind of we can do things, or remotely measure individual heartbeat, respiration rate, and all in a room full of people. These kind of things we can routinely do. So much deeper way of finding the scenes. So all of these are kind of good things, and I broadly we are across a whole range of projects. When I know tremendous work at your university as well, many different domains, and I guess sort of it's moving beyond simple sensing in the past to even kind of inferences to now really a deeper comprehension of the scene and then take actions on it. So all of these are great things. What I wanted to focus on are some of the challenges that sort of arise at this intersection, things that we encountered, and some of the methods that we have found as we kind of approach them. So I have divided my talk into kind of 3 such challenges. And the very first one we'll touch upon is deployment time variations. When we build these IoT systems, every deployment is different. So I would take the analogy like worry about in mobile phones, how there is fragment across manufacturers. But when we go into IoT, every deployment is almost like a new device. It's different. It's different in the environment it's operating in. It's different in terms of what it intends. So like if it's in a mobile, every person is different. It's different in terms of the platform characteristics. So like example, since a lot of inferences they're trying to make depend on timings, timestamp accuracy, location accuracy, things like that, as well as the platform characteristics like latency. So if you are particularly making inferences where real time matters, then again, this platform characteristics comes into. So I want to touch upon a few of these things, and the solutions to some of these are of course system problems. And one of the things I wanted to highlight is that as we talk about AI, IoT, that intersection, and a lot of problems are not simply about the model, but it's really about the system that model is running. So the challenge I want to sort of come up with is this really is that how do we create systems or write AI IoT applications with portable? And so if you think about, like, for example, a lot of what's happening in the field on employing these methods for things like smart building, problem is each one of the building is considerably different in layout, different in the sensor deployment, and also it's very hard to author applications which are um, where we can achieve this goal of, like, the model just run across these different deployments, because just the sensing substrate you are running on changes. And currently, in trained models and all, there are lots of assumptions about that underlying sensing substrate. So, and part of the reason is that the underlying information about the deployment is often not exposed, and when it's exposed, our models don't really sort of have a way of handling these things. So the future clearly has to be one where somehow we are able to write these applications which are code portable. Now, of course, a portability in the narrow sense of being run on different kind of IoT devices, and their technologies like WebAssembly and such have sort of begun to emerge, where high performance and sort of portability of execution. But there is also this issue of portability across deployments, the specific environment that things are deployed in. And this one of the directions that we've been working on, the deployment exposes its characteristics. Please let me know if my audio is not coming through, because I am getting a network instability message. But so please free to interrupt or write on the chat if that happens. So one direction that we have been doing is that deployments with the assist of sensors exposes its contextual state, where the sensors deployed, what the correct settings are, and the domains that we have sort of been examining is building kind of a multi-university effort. This metadata framework called BRIC that has emerged. And also on the health side, we've been working through MD2K Center at University of Memphis in defining these things. Now, part of the challenge in this metadata is, of course, kind of agreeing upon standard things, but other challenge is, how do we self-configure? How do we incrementally update this metadata? The information comes in some cases from human sources, and some cases from sensor measurements themselves. So kind of this original vision that existed in kind of self-configuration, it's kind of at the heart of it, that how do we take this messy, incomplete, unstructured sensor data and then translate it into sufficient information about the deployments that is then exposed to the applications. And that's to the final bit in this kind of story, that this metadata is then has to be ingested by the applications, which then have to adopt to it. So the vision that we've been working towards was part of a center called CONIX, with folks from UC San Diego and Berkeley and a bunch of places. It's kind of this notion that the op system at the IoT edge ingest this metadata, which turn is being from sensory data, and then applications at runtime, application itself being portable in the sense of using WebAssembly and such technologies, but crucially, it queries the platform, queries the deployment, and then tailors to that. So that's the direction that we've been taking. Now, that addresses the implementation problem. It still leaves aside how does the model adapt to the characteristics of the environment, not sensing substrate, but the fact that every building is different, or whatever target that you are sensing object for. So an example of it is from health domain, where as we use wearable sensors, then this variable person-to-person variation, and the challenge is that if you train that almost always the variations kind of swamp out your model's ability to sort of adapt to it. So in this work that we did with who's now at postdoc at MIT, and Jack Stankovic in Virginia, we kind of looked at what kind of approaches work well when you have considerable percent-to-percent variation. The setting is a wearable sensor, which is being used for human-computer interaction through gesture-based interactions and such. And the challenge out here is that even kind of reasonably large training data sets that you would have, you would kind of train to the average, and then the particular person performance takes a big hit. In this particular case, the kind of gestures we were tapping thing or moving fingers, and so essentially sort of interacting with the device with the help of inertial sensors on the wearable in this particular case, and likewise sort of other human activity recognition. The point being, repeatedly sort of we notice that the performance takes a hit on one particular individual. Now, the challenge, unlike vision and such modalities, it's very hard to train for sensory data. It's very label. It's very hard to collect labeled data, and therefore the standard supervised learning paradigm doesn't quite work. So the program we've been investigating and have had quite a bit of success with is, could we adapt new users by making use of the abundant unlabeled data that we have, so without using the label. So in particular, by sort of making use of this unlabeled data and doing kind of in a underlying latent space, we kind of adapt to the new user. But this requires kind of change mindset, that instead of looking at the initial accuracy, so we kind of focus on how rapidly converges to accuracy. So in this particular case, what the figure out here is showing is that we had trained on some modest size training set, a few hundred people, but our new user is missing that, and so kind of learn a mapping between the two, making use of the unlabeled data, but making use of the fact there is still going to be some proximity in the latent space. So we kind of learn that alignment. And then as we learn that alignment, the performance over the course of days kind of improves. So there is kind of a continual learning and or kind of a dynamic that sort of kicks in. The key takeaway from second takeaway in terms of this deployment time variation is really making use of unlabeled data, so that as we are in a new deployment, then over time we converge towards a good level of accuracy. The final part, which occurs quite a bit in IoT deployments, is that time plays a role, and the platform characteristics play a very important role. And very common in of our work really has been that fuse information from different modalities, either the same platform, like let's say camera and acoustics and IMU on your smartphone, but also frequently from different sensors in the same space or on the same person. And the challenge comes is that there's an inevitable discrepancy in time alignment across these things. So certainly across devices, one would imagine that would be the case. These devices are working as a network, and time synchronization is never perfect, and in fact often quite bad. But even within the same device, the pathways of the operating system differ, and we've all noticed that commodity operating system oftentimes do not do a good alignment. So for example, some work which sort of actually ended impacting handling of synchronization in Android was that the way, or until a few years ago, the versions of Android were kind of primarily resyncing error where the error could build. So there's a bunch of devices which are all good thing, but some devices the error would build up and then reset after a while. So they were basically not designed time in mind. And then after we reported it, I think the new versions of Android, from the error being up to 5 seconds, in some cases it builds up to a couple of seconds, but the issue still remains. So as we run these applications on sort of general purpose edge devices, we do face this challenge that timestamping errors exist both within the device and outside the device. And happens as a result is that when models are fusing this information, then kind of they don't live up to the promise because the accuracy drops. So for example, normally, like it's doing some human activity recognition, audio only, IMU only, and the fusion kind of gives us some advantage. But happens is that if the modalities are not well aligned in time, you kind of lose that gain because of that distancing, because particularly for fine-grained activities that we're trying to do. So now what you remember is that time synchronization, often you don't really have control over. A lot of these devices are black boxes, and also really what this is used for is that just like we design our models to be robust to, let's say, lighting and other forms of perfection and data, it's equally important to also make them robust to timing errors. And one approach you might imagine is that as you are training these things, deliberately causing them to randomize exposure to the timestamp error. And this strategy works reasonably well, at least for the of a certain amount of time misalignment that you might see. So that's kind of the approach that we explored, and but it remains kind of deep, and the solution again is kind of a combination of the two, giving your underlying thing and making sure that you have an understanding of different pathways through which different sensor data are traveling within your device. So like age versus IMU versus sound, they kind of go through pathways of different latency, and all of these have to be considered. But additionally, making sure as we train our models, then part of our data augmentation phase during training, we kind of also expose them to now. By the way, please feel free to interrupt me either on the chat or orally to ask questions. I think it's a way to that we have a bit more interaction. Now this kind of a training time domain kind of an approach is not the to do in many settings. So another source of issue comes is that the platform characteristics vary, and so for and particularly important when your model is sitting in some sort of a perception control loop of some sort, a closed loop system, like let's say a deep reinforcement learning type control system. So in this case, traditionally these control systems, the controller designs were based upon first principle, some control theory or modeling of the plant and all. And so if the delays were to change, could go back to our model and then model. So essentially, if the sample rate changes, we know how to change our control parameters, for example. But if we are in a deep reinforcement paradigm, then essentially you have a black box model that you have learned. And now if the delay changes, it's not clear how the weight of the underlying neural network has to change. And very common paradigm in deep reinforcement learning type systems, therefore, is apply action as soon as possible. But what's happening is that the latency of your sensing, computing, and then acquisition pipeline becomes a parameter of your system. And if that varies, the control performance will vary. So I've tried to show it in the picture that if you look at an end-to-end system, then we capture sensor measurement, and then of course there would be some sort of sensing delay. Then we compute the desired action, and that involves model computation delay and potentially sending it to cloud server or OS scheduling delays and also kind of all kick in out here. And then finally, you kind of apply things. Now, normally in a very synchronous control system, we would design these things with a particular periodic schedule in mind, and then we would apply the next instant running the system synchronously. But the common paradigm that has emerged in deep RL system is let's apply that as soon as possible. So the delay is the action, the optimal action now in part depends upon when you are applying the action. And variation in these delays can have considerable variability. A lot of them simply because you may be running on a Raspberry Pi or a Jetson Nano or these kind of devices where multiple things are happening. But then there are also issues like the power management on the device kicking in, throttling happening, and of course, if you are outsourcing to some sort of a cloud device or even a premise server, then again, that delay kicks. And this matters because if you it's kind of a variation across deployments that you would see begins to sort of cause problems. So when you deploy the system where the delay characteristics are different, the system may not behave properly. And here's kind of a second example that we are showing robot where kind of when under the latency for which it was trained for, it's moving fine. But when exposed to latency, which is different, it basically doesn't perform. Because one answer is you could say, okay, why not do it the classical, which is kind of assume conservative delay and then always aim that, but then that leaves performance on the table because you're always going to be running conservatively. So the idea that we sort of pursued and presented at Coral time back is really to make the platform characteristic, the context, if you may, the deployment context, as another input to the model. So the current expected execution latency is often something that you can estimate using kind of the recent history of the platform, and then we can kind of expose that to the model. In a reinforcing context, you can say that we are augmenting our state with not simply the environment state, but also execution latency and sampling interval, or perhaps more generally, some of the operating system and hardware level counters that may exist that you can expose. And kind of the idea, the model is not only learn to figure out the action which is optimal given the environment state, but also kind of the platform state. So as the latency changes, the computed action kind of changes, and that is factored accordingly. So we kind of sort of in context of latency, we call it a time in state. Actually, we incorporate latency as an additional feature of state. And now during training, we kind of train this model under different latency scenarios. So there's still a domain randomization, but the state itself is augmented. And this kind of works out pretty well. We kind of have tried it various systems, simulated and real. This an Amazon racer car, which is our in-lab C4 things, and basically this time in state kind of results in which kind of perform better both in terms of not failing and also finishing quicker. So key takeaway from this side, sort of making and fit your model environmental state is important. So kind of to summarize then, there are things when it comes to these deployment variation. First, of course, is the ability to write applications which have access to the platform characteristics. What are the sensors? Where are the sensors deployed? And that's the role of the metadata. But part of it, this metadata has itself to be fleshed out using inference we make on sensory data. Point that I is that for the model to adapt from one deployment to another deployment, given that it's just too disruptive to ask for additional data on a given deployment, really making use of the under data is sort of considering these temporal dimensions is super important. And I would, while we haven't explored as much, but uncertainty. Similar issues with location information would also be important. As sensor location is incorrect, so errors in location of the sensor or variation that would have similar impacts, although we focused on the time. So that's challenge one, right? Coping with these deployment time variation. Now we're going to take a pause out and see if anyone has any questions. Sorry, my limited screen space. I will. If anyone, just go ahead. Otherwise, I'll move on.
So I do have a question. So yeah, it's very interesting, but I just wanted to maybe understand better, like you know, the timestamp errors, how much you know, it can have a bad impact of the, you know,
Sure.
because I see the examples where, you know, even tens of the millimeters, right, milliseconds can still make a bad impact, right? I'm just wondering, you know, yeah, that's something, you know, I thought it could be a few more seconds, but you know, like even tens of the milliseconds can have a bad impact.
Yeah, so it depends. It kind of depends upon the process that you are either to make a state inference about or control. So, for example, if I'm doing gestures like flick of a finger and stuff like that, milliseconds matter. If on the other hand you are doing things like walking and all, which can last for long periods of time, then the threshold is much higher. But what we notice in some of the platforms, because of certain system issues, errors often build up quite significant. On the control side, milliseconds matter because even mechanical systems are stopped at sub-second type sample periods, and also the kind of variations that we see to of millisecond, order of tens of milliseconds play a role out there. So I don't think we can answer this question in the abstract, but sort of relative to the phenomenon. In other settings like military sensors, a bit about the synchronization thing. So like if you are collecting IMU or seismic or these kind of data from across different sensors, the kind of tapping that current networks are able to provide. So using TP, for example, over these networks and all, you're going to see or tens of millisecond type errors, and they begin to matter. Latency variation, of course, is a function of the platform. A trend indeed has been towards moving to kind of general purpose edge devices as opposed to kind of real-time operating system running on highly controlled environment. Therefore, on hand, baseline performance in terms of throughput is improved, at the cost of more variations, and that again sort of begins to cause. So at least for these kind of bots that are, let's say, order of 100 hertz type sample rate into significant degree in performance with kind of variations that we see. Now, I think the answer to this in part is certainly better platform, but I would also argue that some of these variations are going to be with us. Like, for example, as we begin to move control into cloud services, that begins to bring more variation. I think some of the macro trends in terms of how we design these systems are making the worse. On the other hand, certainly totally slate design and limited, one could mitigate all these things from at a system level too. But just something to sort of consider. On the location side, we haven't studied as much, but not hard to currently location ability to realize things even with sensors which are indoor is of the order of tens of centimeter with sort of very good instrumentation infrastructure, and again for kind of inferences that would introduce there, but we haven't studied that.
Got it.
Okay.
Thanks.
Okay, so let's move on to kind of the second thing I wanted to cover was the need that we should combine data that we collect with first principles knowledge. I made kind of this point earlier on that kind of our IoT, if you look at papers in our conferences, let's say around 2000 to 2005 timeframe, they were all kind of first things and all. And if you look, or very simple sort of data-driven models. And now if you look at recent conferences, they're all about deep learning meets IoT and shape and form. I think you call AI ML conferences with just more of a sense of data on it. I would like to argue really both important and just go over it and why is so. So obviously, sort of the adoption of neural networks, like I already sort of figured out, is letting us sort of pretty amazing sensory data, whether it's acoustic event, stuff from IMU, and of course from cameras, excellent at detecting, classifying, particularly kind of activity over which are relatively localized in time and space. Okay, so transportation modalities and sort of what's one doing in that bin and fall detection and things like that. This kind of things we see all around. A couple of problems, and for which sort of argue for perhaps sort of rethinking that only neural network kind of the way to do. So one is sort of the question of explainability and tellability, which as we create these systems, we do still need to make sure that they adhere to certain regulations and trains and sort of laws and tax procedures that may, and more importantly, also perhaps potentially benefit from physics that is already known, so that we don't have to rediscover that physics from data. So that's us tell our systems what we already know or what we want the system for sure to adhere. And the flip side, which is sort of interpretability, scalability, but this is kind of part of when things go wrong, then either the designer or the end user, whoever the operator is, able to see what was happening in that sort of model which was processing the sensor or taking the actions. And all of these challenges to do with data-driven models. And I would also mention that this is not simply because the data-driven models, neural network large, even with smallish models of issues. On the hand, with physics-based first principles models, that these things were not an issue. You're learning how to process speech, signal processing classes, or how to train controllers. There's kind of an underlying physics understanding which made these tasks really easy. Second part is, those models excel what I refer to as atomic events, as in events which are relatively localized in time. When we start thinking about complex events, complex spatiotemporal events involve large spans of space and time and multiple agents and all, then a purely neural approach, at least currently, is pretty tricky to do. And actually, I mean, if you have followed the discussions around things like ChatGPT and all, they're kind of bringing out the same issue. Even these large language models have limitations in terms of the context of reason and all. Here I've shown an example. Imagine in a hospital, this is instrumented. We want to do some sort of a sanitary protocol or hygiene protocol. So unless who sort of forgets to wash hands and sees another patient, we want to flag these things. Similar things in other contexts, in a free or a restaurant or things like that. So out here is that there exists systems where whether a hospital setting or airport city or traffic systems and all, we want to connect the dots across sort of events which are happening asynchronously, irregularly in space and time by different locations, and sort of there is no sort of structure to it. We want to detect things like someone staying in your house and kind of thing. Of a different flavor, what was happening over a short time window, that someone fall or was making a sandwich, things like that. What this requires really is both an ability to perceive short time scale events, atomic events, if you may, but do so from unstructured, high-dimensional, noisy data, which we use in network, but also at the time be in an IoT context, be able to reason over these events over large time scales. Was a traffic policy violated? Restaurant worker not follow the hygiene call and things like that. And I would also like to mention that this is not simply like we can say, oh, this is just a bunch of sort of a bag of simple events. Taking the analogy from bag of words kind of models in natural language. Here, again, much like natural language, things like sequencing and count and frequency and all these kind of things matter, right? I mean, I can take the same and different permutations of them small to different complements. So this we clearly have to reason about them more. A point to note out here is that this kinds of discovering these kind of complex events, normally we do using finite state machines and some sort of systems like that. If we were to try to do them purely, it requires context, lots of memory, whereas our current models have limited context, have limited things. So I've sort of given examples out here of different kind of models, convolutional, LSTM, and convolutional models are time window, it's going to window, transformers, similar story. So once we are talking about long time scales and forget about sort of stitching data from multiple different sensors and all, data limit. One thing you would notice is that we're kind of talking about across all these models, 200 to a small number of thousands and samples, right? So like ChatGPT, for example, with 8,000, a context of around 8,000. Most of the models that you find with sensory information and sure, they work great for kind of small time windows. The problem is that if you're working with sensors and trying to detect the kind of complex events I'm talking about, you will need vast contexts, which basically are beyond what we are currently able to do. So what requires, and I guess in other domains also, where reasoning versus sort of more instinct people are sort of exploring this combination of sort of neural and sort of principles as models. So deep learning models have advantages, particularly sort of the fact that can with their tensorized implement accelerate them. They kind of they can work very well in making inferences for which we can't really express rules very easily with sort of first principles model. On the other hand, kind of they have the issues that we kind of pointed out, and symbolic is one other. There's nothing new out here. The point is somehow we need to kind of what asking for is really some sort of a combination of the two. In Daniel sort of world, this is like system 1 and system 2 overall thing. So so that's the idea behind Neurosymbolic. Now, a few years ago, as part of my work with Army Research Lab, sort of collapsed there, we kind of started looking at this because in military settings, these complex events are super important. At a single instance happening in the battlefield can be very minimal, but when you look over a bunch of sensors from different parts and over a period of time, then you begin to get the sense of what that we might be doing. Our context is military, but similar issues, like I said, occur in other settings also. So we kind of started looking at this thing with systems. The perception layer was being handled by deep learning models, but then some sort of logical model which is capturing the knowledge about the kind of components and be able to sort of make some inferences or reason over them. So this is where the human rule and the rules that constitute the task and procedures and knowledge respond to complex event component. This is kind of the pipelines that we begin to explore and different ways of these things. Initial attempt for a system called that had done this is like 2019 time. It's just kind of a feed for system. Nothing, at some level you can say that our layer one is things like YOLO 5 and all, that something that gives us access to what exists in the scene, and then using sort of some domain-specific language and all, we kind of would create automata which would sort of add that. So kind of straightforward, feed-forward line, just to see what benefit, what would be the right part between two things. But the more our interest, how do we design these kind of pipelines, right? I mean, assembling one such pipeline, not a big deal. How do we do such pipeline? How do we train? Have additional data input could be, how do we input that, right? So could we make use of knowledge and data in these kind of context? So we started by simple approach, reasonable, essentially create a new C. So given that second layer, the logic layer, essentially would translate that into a stateful current neural network model, and we have an all new model, and get some additional data about some complex event. We can kind of backprop and this thing. Let's issue some sort of the that can handle and all, but at least settings where the deep learning model was giving us usual object classification detection of things, and then sort of we are looking at some patterns like a bag left unattended, a nurse washing hands, those kind of things we begin to handle. So approach one is this neural C approach, and going from sort of or finite state machine type description into neural was kind of the key enabler out here. What it and tried it on sort of right of some patterns over image, but also like activity, acoustic event. And there are a few things that we kind of that first these kind of tips versus purely neural pipelines, right? Less faster, that and with better final eventual performance. So in this particular case, the Neuroplex, two versions of Neuroplex sitting out here, they're kind of much better models. They learn well with limited data. That's the reason, right? Kind of incorporating already knowledge about what constitutes complex event into the logic model. So we would expect that particular sparse data setting, that's a big plus. And again, our context will not that, but generally speaking, complex events, the more complicated phenomenon, is likely that you will have less data. Form much better in the base, so the scale length. By that I mean that if I at complex events which manifest over longer timescales, then again do very well. So that was great, but there is this neural proxy element which has the issue that as you go from tools to neural net, then perhaps we are not maintaining all the fidelity. So wouldn't it be nice if we could train the rules exactly as they specified? And that led us to sort of a second approach that we pursue and recently out in a work with collaborators at me and also Cardiff University. So this leverages recent versions of what are differentiable logic. Sorry for the typos, should be differentiable logic. So we differentiate, like you differentiate models. We can backpropagate. And this is where one of the systems, which is from US 2019 or 2020, called DeepProbLog. So it's basically a probabilistic logic system, but it allows for new gates. So it now gives us a framework where we work logic using then we can propagate. What we did was exploiting that. We basically created a event layer so that we can express different events and apply it to multiple setting and all. So also two approaches: differentiable logic approach, the new proxy approach. In case of differentiable logic, the advantage you have logic and learnable parameters. There's no approximation at training. At this time, both are the same, but at the training time, the computationally complicated. I mean, in part of the reason neural networks won over symbolic method is that computationally they scale much better and that, and you can have them out here that even if inference costs blow up, that is changing. So at this point, there are symbolic systems emerging, which basically translate them to efficient arithmetic circuits, which you can tensorize and use of the GPU and kind of. So there's a positive element there. So I think balance is continually shifting. That's that. And some key takeaways from this is neurosymbolic models do allow human knowledge for the whole advantage in some of the elements that I mentioned, which is sort of sparse data kind of a setting, complex event, those kind of ability, large context and so they are also inherently more explainable because the neural symbolic interface that I described, you can think of it now. My final decision can be action or decision can be expressed in terms of what and that at that layer. But there are certainly issues which are unexplored in terms of training these things, as well as are they actually results actually indicate that these kind of models are better in terms of adversarial reports and such than advantages as well. Stepping back, what I described is the approach which is kind of one point neurosymbolic landscape that exists. So describe neural, right, perception, reasoning, but there's a whole bunch of other things, and some of them actually, if we kind of reflect back, we already use. So following symbolic is something that we do when we have human engineered features, right? Feeding into a neural network, and which is still the case in many domains, including a lot in IoT. Aggregating and fusing neurons. So, for example, both you can think of in some cases an ensemble model. It could be different parts of your system are being predictions are being handled by a neural and a symbolic model, and then they're fused in some manner. Of the needed setting is that I want to train a network to have it for some constraint, but some sort of a stick constraint, some operation, for example. And those rules are typically, so after we are training the neural network, we also want to inject semantic philosophy, symbolic expressed. And at some level, you could think of it as related to this neural followed by solve. But for example, my colleague Guy Vandenberg, a system called Pylon kind of lets you PyTorch model, but where you have arbitrary function, the regularizer. Neuralistic symbolic, something where you have a primarily symbol based model, let's say something you're designing control your thing, but maybe some elements of it where maybe some variable whose physics is hard to model be done neurally. So in this case, the neural components become kind of a subroutine call if from within and more generally, you can think of that our systems could be viewed as some sort of computation graph. Some nodes are neural models and some nodes are symbolic models. Just to give you an example, well, actually, this So perception, reasoning, oftentimes we have like trackers, Kalman trackers or particle filters of object detectors. In some recent work, some paper coming at ICRA, load neural inertial navigation. So this in context of agricultural robots, tracking them in agricultural resource tiny robot and some strawberry farms. And here what we do is take an overarching Kalman filter, but then some elements of this Kalman filter are expressed neurally. So the kind of idea between input U, these are the sensor in to the state X. So is done neurally. So because the physics are kind of hard kept, out framework is all Kalman and therefore symbolic nature. So wrap that part up, I think this richer land neurosymbolically sort of gives, and then particularly in IoT with complex events and sort of considerable sort of physics models that already exist. Sort of we have and well, so math is so before the challenge, I want to pause and see if anyone has questions.
Anyone have a question? I don't think so.
Anyone? Let's move on then.
Yeah.
Finally, in case of IoT, it's super important on edge devices, right? I mean, a lot of IoT is really the sort of edge all the way to the cloud and complex multi-tiered cutting substrate on which we are doing things. Test offerings from the various sort of providers. You have edge devices, you have premise servers, you have sort of edge network servers like some base stations and ISPs, and then finally the cloud. 3 or tier type computing structure, and then we distribute across. But key part of it is what's happening the kind of very edge part. Oftentimes because latency and connectivity prevented, often privacy considerations and all as well. So so while sort of neural models and neurosymbolic models, which incorporate neural, of course, provide a lot of advantages related to pure small models, oftentimes implementing them extremely resource a challenge. We can do them on what I would call higher end IoT devices like your smartphone and Xavier and those kind of like mini Linux boxes or Unix boxes things there. But the moment we go to microcontroller or microcontroller accelerator, these kind of devices, suddenly we are looking at mods that have to be a lot tinier, in hundreds of megabytes or even gigabytes, really tens of kilobytes and all, and how do we sort of handle things there. Now, this is with the ML. Now, I'm sure many of you have heard of it, which is referring to devices has emerged. So I'm going to talk about what sort of some of the limitations of current flows are and sort of what we have done, but just what the promise holds. So let's examine, for example, a very common use IMU sensors, which is for bots use for UAVs, use it anywhere where either you don't have access to GPS or you predict access to GPS or map information. Often rely on this inertial odometry. And here we kind of really have recently really kind of two choices, if you may. One is we can go purely symbolic methods, purely physics-oriented methods like filters. Now, they don't perform well, even though can be fit into our tiny devices. They're extremely resource efficient. So, for example, we double integration or recurrent systems, but the errors are pretty bad, as you can see. Alternatively, over the past 3-4 years, we have to see people neural models. They have much better the error numbers out here, much better than physics counterpart. Then they require lots of memory. If you're running on a Raspberry Pi stuff, if you're running on a microcontroller. And unfortunately, frameworks like TinyML, interns built on TensorFlow, really kind of take care of the low implement part of it. Really kind of this sort of the architecture that needs to be done for thing on a particular platform still kind of leaves open. So if you look at sort of the current design flow, the way it works is TinyML kind of provide you TinyML type tools provide you limited, then below that with model zoos, architecture search, then into platform, and there are lots of issues that currently exist. Firstly, of the NAS, these platforms that exist for architecture search, they really don't have particular knowledge of platforms and the uncertainty, and also they really guarantee implementation occur at the end. Moreover, presentations that they learn, they're purely neural, so they have to incorporate essentially they don't have some type approach. Limited text memory, so again, complex event kind of stuff can't be done. Finally, kind of to keep things manageable, they kind of usually read in architecture. So what we have done over the past couple of years, there's work in collaboration, partly with ARM, partly with STM, looking at sort of really providing a pipeline with platform there, as in really what comes run on your platform, some proxies, and really gives you run code, which is tuned your platform. And second is not neural, but really looking at this specific case of neural and symbolic, which are bundled together with the application. So yeah, starting point there was based optimization framework. So you download it on this website called Mango. It's out here. So that's the underlying framework. ARM uses for optimizing chip design and all. Then we have been using them for IoT systems also. On top of it, then we have created a system called ThinkBase, provides tiny hardware. Initially, what it lets you do is it's a great free, so it lets you model a lot of hardware constraints, flash memory, how much performance environment you have, how much SRAM you have, kind of a lot of and then just given a parameter backbone architecture, it searches through that architecture space. Crucially, in order to avoid any uncertainty in eventual performance, instead of using a proxy model with all this uncertainty error, a hardware in the loop. So as the optimum is running, actually encodes, runs on a hardware platform, takes that feedback, and then so we are using for multiple domains. One paper we published last year at IMWorld, Tiny Odom. So this is optimized neural things. And long story short, with this approach, we created systems which far beat anything which was previously stopped. Again, not because we were clever, but because we so similar error, but much smaller footprints. So essentially, we kind of brought the work models to control type here. So that's one area. We similarly did for what we auditor. So this is what models running on in-ear type device. In similar story that smaller models and more accurate. So I guess the takeaway I would say is that humans may be doing these the kind of we have better job basically. And the other thing is it gives some flexible, much like you're designing a chip or an FD, you can play, we can say across microprocessor choice, microcontroller choices, we can get design. It of course requires GPU merged with the hardware and the loop that we run. So we work with embed-based platforms, so that's what we currently target. Something we also learned in this process is when we compress models down to these tinier platforms, they do come at a cost. And in particular, these tiny models relative to models running on the higher end IoT device size models. Two things. One is less domains. So if we take this Hyper-T model and then apply it into different contexts, say we in inertial navigation type to kind of vehicle, they become more brittle. Another one is for backward. This is kind of an interesting, which is you may be improving performance of the model as you do some of these optimizations, but it turned out that some test points where giving correct results, it no longer is, or vice versa. Average is improved, but if a specific input is important, then suddenly there will be unexpected failures. From a customer's point of view, my starting will be longer, even though manufacturer is better overall. And so we find that also that lighter weight models, kind of these two metrics are also important and something to consider. Lately, in paper currently in submission, we have extended neural architecture search to a neurosymbolic architecture search. Take entire symbolic structure kind of from that richer landscape that I shown there. So essentially, you can think of the neurosymbolic model as kind of a you're doing a search over that, and enhanced thin-based platform, something TinyNS, which again does the same platform in web, but for symbolic stuff. And with that, again, we have been applying it to a variety of pipelines, like, for example, co-optimizing a neural object detector like YOLO5 or similar things with a symbolic. So oftentimes this task is done by humans. We have really these two parts of the system and prove the accuracy of the neural part, then tune the symbolic, and it's like days, like many hundreds of hours of effort of a typical human, sort of doing repeated simulations and things like that. And 3 GPUs, unfortunately, we have low GPUs, but with GPU fast, we get comparable results, like 4.5% higher performance with actually smaller footprint. So we are able to do these in with our framework. Again, you need embed enabled type microcontrollers, but that's more of a software engineering constraint. The ICRA work that I mentioned on neural you have kind of a neural module which is embedded inside an Kalman filter. Again, the same kind of an optic one has again the full sort of human design problem. We are able to, with this stuff tool, we are kind of able to explore this whole architecture pretty well. So that's a third piece of our this tool actually is already on GitHub, and convinced to us someone from ST Microelectronics discovered it and put it on LinkedIn today. So so NS is kind of our piece out there. So closing thoughts out here, sort of, I think we've really been looking at these 3 different aspects AI IoT sort of nexus. The issue of is the part bring out is beyond normal sort of work is issues of time and space and characteristics and sensification are particularly critical for IoT, and somehow making our model systems both robust and across them. Second thing is that while purely neural models are doing absolutely wonderful things, but IoT complex events and more complicated rules of operations and all are fundamentally covered. And so when things fail and the data are not humanable, so explainability becomes even more important. So combining logic together with the neural is super important, and then having that being part of our arsenal. And finally, is talking about these extremely resource devices, having appropriate the counterpart of what high-level synthesis was in chip design, kind of this NAS intimate or neurosymbolic architecture tools like TinyML really is where another feature is, because these optimization tasks are way too complicated for expert system to do or expert people to do, let alone kind of sort of people who are really interested in their applications. Many unexplored questions at this entry. We are headed into sort of this territory where we are running things out in cloud service or as multi-devices. The role of accelerators in these devices, challenges relating to these other metrics like bird compatibility and such, and then of course issues around security and privacy sort of are less explored in these systems. So I'll close by saying that sort of way I kind of think about where this IoT kind of interface are headed. I think currently stage where we can create assignment systems which are designed for a particular domain, a particular relatively well, but with a lot of pain. Requires lots of but there's very interesting stuff with it. And if you go to our conferences, kind of, but we are not able to engineer systems so that they work in more complicated inference. Right now, it's more complicated inferences are also something we are very poor at, certainly not under kind of extremely limited. And sort of addressing these, I think, would require both model applications, our sort of our platform level, and then very critically all the tool level implementations, because the kind of stuff we need to do with these models is kind of different from what sort of big models, language models and all trying to do running on GPU and also are what different, and our embedded design pipeline has to change accordingly. So I'm going to say that a bunch of papers in the pipeline in terms of at various stages, and also a whole bunch of industrial and funding agencies have sort of supported us on journey. So thanks to all of them too. So stop and take on the part of the talk.
Thank you very much, Mani. Any question from the audience? I think any question? Yeah, I see somebody raising his hand, please.
Thank you very much for the wonderful talk. I just have a quick request on the slide 52.
Slide 52. This one?
52.
Yeah, sorry.
I guess 51, sorry.
Well, the newest slide. Am I going in the right direction?
Oh, yeah. So here, you talk about the,
I think it's page 51.
51 years.
Hmm.
Yes, this one, the neuro-symbolic model.
Mhm.
So here you talk about the architecture search for the um, neuro-symbolic model. So I wanted to ask if you have like a published paper that address this topic.
Or you have pushed the paper? No, what's the question?
Yeah, I mean, like it's a request. It's a request. Do you have like a paper that
Oh, yeah, paper is in submission to system, but if you write to me, I'll be happy to share it. A preprint. Yeah, it's not on any website right now. The submission, I can start.
I can't hear you well. Maybe I send you a chat or something, or you send a
You
chat.
can you send me an email?
Oh yes, sure. Can I
Sure.
have your email, please?
Yes.
I can forward the email to you.
Oh, okay. All right. Thank you.
Oh,
Yeah, just
yeah.
send me an email. Also, I can send you a link. It's public already. So yeah,
Okay. Thank you very much.
sure. Yeah.
So any other questions from the audience? I think I have a general question about, I think really echoes with what you summarized in the last few pages of the presentation. I think, you know, on one hand, we have this very limited resources on the IoT or edge devices, but on the other hand, we have this extreme challenges, right? You know, for robustness across different environments or deployments. So it seems to me that this is kind of like a very challenging problem, because we do need more resources, right, to tackle with these or to enhance this robustness. So yeah, I think do you have any yeah.
Yeah. So certainly risks are a factor, but oftentimes the reason they are not robust because during our optimization, we don't factor in those requirements. For example, now that we have the neurologic framework, one of the things we also do actually is in the paper is that we are able to optimize. Remember, I said that one of the forms is you are training a new for symbolic constraint.
Mm-hmm. Right.
So we have to train it in. So when it searches for a tiny neural net position, it searches for one which satisfies certain robust, including things like backward compatibility and also. Okay. So I think some of it is having the right tool support so that you can express this. In the absence of that, as a plain human designer, it's super hard. But of course, larger models will have better characteristics on a lot of these things, needless to say. Probably attention is a big part of the struggle, which is a small model is there, but maybe we can switch one model to another settings and non-volatile can be part of that. So this loop and we can switch to that. So adaptation would perhaps be another story. So it's I think it's more about the awareness right now that nothing comes for free, and I think there's a lot of focus that we put on average accuracy as opposed to the other measures which are typically important.
I see. So basically, incorporating those factors when you design the.
When you're planning your optimization, I think that will have to be tools. I mean, look, graduate sprint days, I used to work in VLSI CAD, and that world was transformed as tools under a lot of theory. And we are now suddenly designing these things with neural model, a bigger complicated IoT program. We really do need to begin to adopt think higher level, then we kind of just. I would say, if one message really is, I think the community really kind of eager for right design tools for these. This is what I think we really need.
Got it.
And so resources, of course, help, but less. The one resource we will need is memory, but memory is very power hungry, and memory power does not go down easily. So I think if we look for resources, the answer, they're probably not some interesting impact on. So I think it's the other aspects which are probably going to play a more important role in the short term.
Got it. All right. So any other question from the audience? I think we are quite, we're already out of time. So any other question in the last minute from the audience? So if no, let's thank Mani again for the wonderful talk. So we will have the video to be uploaded on the websites of the OSU IoT seminar series, as well as the NSF AIH website. Thank you everybody again for attending the webinar, and we'll see you again next time. Thanks so much, Mani, for the wonderful talk.
Thank you. Bye.
Thank you. Bye bye, everyone.